Okay, so this is what the Lewis theory said. Lewis said that each hydrogen would have its own electron in an orbital, and this would be another hydrogen in the orbital. And these two would basically come together, and they would form a new orbital, and this new orbital would have one electron that would come from one of the hydrogens, and the other electron would come from the other hydrogen. So this would be the bond between hydrogen. It would be represented by the overlap of the two individual orbitals. If we look at hydrogen fluoride, everything works out fine. Again, hydrogen is like it was in the first case. For fluorine, the configuration is 1s2, 2s2, 2p5. So just looking at the 2s2, 2p5 part, you have your orbitals. You have this filled S, and you have those that are filled, and then you have the half-filled. So this half-filled would overlap from, or with the half-filled from the hydrogen. So this one would be from the hydrogen, this one would be from the fluorine, and then the bond would be formed, from those two. Okay, so everything was fine with those two. So next we try the same idea, but this time we're going to look at beryllium chloride, or beryllium dichloride. So the configuration for beryllium is 1s2, 2s2. So right off the theory doesn't seem to work because we have this orbital and it has two electrons. So in theory it shouldn't be any sort of hybridization. So remember that we also have the p orbitals available. So the idea is that these two orbitals hybridize, and one of these electrons here moves up like that. So then we end up with two, and these now are referred to not as an S and a P, but two SP. These are called SP. Okay, so when the bond takes place, so when we have the half-filled orbital from chlorine, it goes in here like this. Okay, so that's SP hybridization, and the AXE form, by the way, is AX2, and the shape of this one is linear. The hybridization for BF3 would look something like this. So boron is 1s2, 2s2, 2p1, and we know it forms 3 bonds. So what happens in this case is these electrons rearrange and form 3 orbitals that look like this, and each orbital has a single electron. So this is a combination of one S and 2 P's, so this one is called sp2 hybridization. Okay, for the hybridization that occurs in methane, CH4, we have the configuration for carbon, which is 1s2, 2s2, 2p2. So in this case, these 4 electrons are going to spread out, and what you have to begin with, I'll show the sort of before and after on this one. So in terms of the orbitals, you start out, and this would be the 2s2, and then you have the p orbitals, and they're like this. So you go from that to 4 orbitals, each having a single electron. And because it's a combination of 1 S and 3 P's, this one is called sp3. Okay, so here are some animations that show the different hybrids that we've talked about. This one is the S and P orbitals forming an sp hybrid, or 2 sp hybrids, and the shape for this one is linear. The AXE form would be AX2. Then next we'll look at sp2. sp2 is a combination of 1 S and 2 P orbitals to make 3 sp2 hybrid orbitals. And the shape of this one is going to be trigonal planar, AX3. Next is one of the most common of the hybridizations. So this is a combination of S and 3 P's. So that gives 4 sp3 hybrid orbitals. And the shape of that one is tetrahedral. Then we have two types of hybridization that accounts for the expanded octets. So the first is going to be a combination of one S, 3 P's, and a D. So this is called sp3d hybridization, and there are 5 of those orbitals, and the shape is trigonal bipyramid. Okay, and finally we have the combination of one S, 3 P's, and 2 D's, and this gives us 6 hybrids. Each of them is called an sp3d2 hybrid, and the shape here is octahedral. And then finally there's a chart, and the chart that I'm going to show you just sort of summarizes the information that we've talked about. So the chart has all of the types of hybridization, the orbitals that make up that hybridization, and the shape that corresponds to those. Okay, so now we'll look at SO3. So SO3, we have 6 valence electrons for the sulfur. We have 3 times 6 for the oxygen, so that's a total of 24. I think probably at this point you can figure out, hopefully, at least maybe by playing around with the structure some, that we're going to end up with something that looks like this when we spread the rest of the electrons around. So if you're counting, it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. Now, one thing that you should notice at this point is that we would have resonance with this, because we can imagine that the double bond can be here, like it is in this case, or over here, or we can have a structure where the double bond would be there. So we would have 3 different resonance structures, but I'm not going to draw those right now. Instead, what I want to do is figure out the hybridization using the rule that I mentioned previously. So I'm going to start out and I'm going to say, alright, I know that this molecule is trigonal planar. When I say I know that, I mean that experiments show that. Okay, so I know it's trigonal planar. And I know trigonal planar also corresponds to AX3. Now I'm going to count and get the hybridization. So if I do this counting, so I count 1 there, and I count 1 of this double bond, and I count that bond. So that gives me a total of 3, and 3 would correspond to sp2. The other thing that you can notice, which is helpful, is over here, if you take the total of the X and the E numbers, like this one is AX3, so the number is 3, that also is going to correspond to the type of hybridization, because this would be S1, and then this would be P2, so that's a total of 3. So however you look at it, you can get the hybridization.